Again, these are major announcements here. Again, you don't have school tomorrow. There's no advisory tomorrow. Therefore, I am making the next asynchronous assignment due on Monday. Course. All right. So let's jump into that recap, everyone. Big idea recap from yesterday, right? Yeah, that was yesterday or the other day. What were the big ideas? So first off, we built these right triangles inside the unit circle. And when we built these right triangles inside the unit circle, we noticed that the side lengths of the triangles had a connection to the coordinate points that we're seeing on the unit circle. That's what we noticed in the Padlet. Specifically, someone did notice that this point, oh, and these were the special right triangles, but someone specifically noticed this point right here, which is the second bullet point. Specifically, how are the sides of the right triangle related to the coordinates? It's actually going to be this. This is the basic point of that idea about the side lengths, but more specifically, the x coordinate is going to be the cosine of your angle, and the y coordinate is the sine of your angle. We're going to be doing some examples today to finally kind of apply that. Now, I am fully aware that you had some Khan Academy practice on this. So maybe some of you kind of had some practice on that. But today we're going to spend some time to actually talk about it. You'll have some space to ask questions. So again, this is your x coordinate. This is your y coordinate. What this second bullet point is saying is that the sine of 30 degrees, the sine of 30 degrees is going to be my y coordinate. So the sine of 30 is 1/2, whereas the cosine of 30 degrees would give me square root of 3/2. And by simply using my unit circle, I won't need to build these right triangles anymore to figure that out. The unit circle will be a resource for you to just look at and be able to determine what are some key sine and cosine of some key angles. That's how we're going to be using this. So that's a little recap about what we found out the other day from these special right triangles. Let me clear up my screen. Again, feel free to put in any questions or anything, but right now we're just doing a little recap. The other part of my recap was the fact that if we knew the coordinates in the first quadrant, right here, so if we knew this, the strategy was, well, we could simply reflect these points to get the other points in the unit circle. What do I mean by that is simply, you would have to know the signs of each quadrant. So in quadrant 1, you have positive, comma, positive. Quadrant 2, it's negative, comma, positive. Quadrant 3, all your coordinates are negative. And in quadrant 4, you have positive, negative. So if, for example, if I was to take this point and I reflect it across my y-axis to get this point, all I have to do is repeat the same coordinate points. The coordinate points themselves are the same. The thing that's different is the sign. And I would just look here on this chart and know that, okay, the first portion or the x value is going to be negative in this case. And then for this to reflect down here, so this would have to be reflected across the x-axis down here. This would create your new point. Again, the points, oh my bad, 1 second, that does not reflect to that. We have to do a direct reflection. So this mirror reflection, right, y'all, goes here. There we go. Now the points are the same, except the sign is going to be different because down here we have negative, negative. So see, that's a direct reflection. Think about a mirror image. So there was a little self-correction there. Let's see. Does anyone have any questions about this recap about how to reflect the points after I just did this little example? By the way, if you just came in, please let me know in the private chat. I did see 2 folks come on in. So I could mark you present. And welcome, y'all. I'm so happy to have y'all here. Okay, so if there's no questions on this, I'm gonna go ahead and clear my screen. And And we're going to go ahead and finally kind of apply these big ideas into something that we can use. Or it could have helped us, if we had this tool for the Khan Academy. And again, the big idea here was that you can obtain the rest of the points in the unit circle by simply reflecting the values in your first quadrant, kind of like a mirror. You reflect it over either the y-axis or the x-axis. Okay, let's get into the application. So basically from those big ideas, how do we actually apply it to do some calculations? Let's do this. So in this first example, I want you to notice you're being asked sine of a radian measure, cosine of a radian measure, and sine of a radian measure. Don't be afraid. We're still going to apply our big idea here. No problem. Yeah, if y'all are having Wi-Fi problems, that is okay. That is understandable. Let me just go ahead and update the attendance super quick. Boom. Okay, there we go. I think I'm fully updated on who's here. Okay, so here's what we need to know. Okay, so this helps me because the big idea said that sine is the y. I'm just going to put a y above the sine. Big idea said that sine is the y coordinate. Okay, cool. Cosine is my x coordinate. So for the next one, I have to look at x, and then we're back to sine. So I'm going to put y. That there is just going to kind of help me focus in on what I should look at. Okay, so next thing, after I kind of label what I'm looking for, I'm going to go and use my unit circle. So notice, so that's my resource. I'm going to look at my unit circle, and I'm going to determine for the first one. The first one is saying 5 pi over 6. Remember, y'all, a radian is another way to measure an angle. So we're still looking at an angle on the unit circle. So where is 5 pi over 6? If we look around, I'm just looking for where the radians. I'm growing counterclockwise as usual here. And I find that 5 pi over 6 is right here. So I'm just going to go ahead and circle that whole portion. This is where my 5 pi over 6 is at. It is also equivalent to 150 degrees. But what I'm interested in is what is the sine of 5 pi over 6? AKA, what is the sine of 150 degrees? That's what I'm asking in degree mode. So I'm going to look at my coordinate. I'm going to label the points. This is x, this is y. So if I'm just looking at the y value of my coordinate point because I'm being asked about sine, my answer is going to be that the sine of 5 pi over 6 is simply 1/2. See, that's how I'm applying that big idea here. We're just looking at the sine. So I'm going to go ahead and write this in. So this is not typed out in your slide, so you definitely want to make yourself a little comment or something. But this first one here we got is 1/2. Let me pause for questions. So this was the first example on how to do this or apply the big idea with a unit circle. Oh yeah, yay, thank you, Janet. Actually, I didn't see your comment. Thank you, you got it. Yes, it was equal to 1/2. Perfect. I'm gonna check the chat for this. Okay, now everyone, let's go ahead and repeat this process, but now it's gonna be for cosine at pi. So I know that cosine means, according to the big idea, that I need to look at the x value of whatever degree measure I'm being asked to look at. So first I gotta find pi. So I go around my unit circle and I find where is pi at, and I see it right here. So it looks like pi is equivalent to 180 degrees. And I'm gonna go ahead and circle my point. I'm going to label them as x and y. And now I'm going to apply the big idea. Let's see what's in the chat. All right, look at Janet, y'all. So Janet says it is -1. I have to agree with you, Janet, because look at the x coordinate at pi. It is -1. The x coordinate is -1 there. Let's see if anyone has questions so far. So this is how you use your unit circle. So if you, let's say you didn't do the Khan Academy practice yesterday, or you were confused, this is how you would do it. You just need to have your unit circle open and you're looking at it as you're answering these questions, because what you're being asked to do is applying this big idea. Yay, okay. So again, let me see. If there's questions, feel free to just put them in the chat as I'm going. I'm making sure to check the chat. let's go ahead and do the sine of 2 pi. So 2 pi, we could look for it, or if you remember, 2 pi is basically the length of your whole circumference or your circle. So 2 pi is basically equivalent to 260 degrees. Now this point is interesting because this 2 pi and 360 degrees have the same coordinate point as 0 radians and 0 degrees because they're at the same location. So you start there and you end there. So it makes sense that they have the same coordinate point at that location. Now, I'm going to go ahead and label my points. And this is asking me for the sine. So that means I'm looking at the y. What is the y value at 1, 0 here? What would be my answer for this problem? And this would be for anyone. So feel free to answer in the chat or you can unmute. What would be the y value here in this coordinate point that I have circled? The y value tells me the sine according to the big ideas. Okay, yes, I got this as a direct message. It is 0. That is right. Thank you so much. Awesome. I love to see this. Boom. So that is how we get the answers for these questions when we're being asked to evaluate. You can use your unit circle and apply those big ideas, those patterns that we saw with the sides of the right triangle. These patterns are showing up with how we're using and answering these questions on the unit circle. Let's do one more set of example. In the next slide, we're going to be doing degrees, and then we're going to move on to our mini group work. Okay. So then in our next slide, slide number 7, I am on slide number 7 for those following along. And we're going to be doing the same thing, except now in degrees. The process is going to be the same though. So except instead of looking for radians, I'm looking for the degrees. So over here, first off, I know that sine, according to the big idea, means I'm looking at the y coordinate. Cosine means x coordinate. Sine means y. So I'm going to go ahead and just do this as a run through. Feel free to use the chat or unmute if you'd like to participate and share with us if you have an understanding of this. But here we go. So 60 degrees. So my next step is after I've labeled whether I'm looking for X or Y, I'm going to go ahead and find where is 60 degrees. 60 degrees I see is right here. It's in the first quadrant. I'm going to go ahead and circle its equivalent radian as well as its coordinate point. Nextly, in my mind, I like to label the X and the Y coordinates. All right, we have an answer there in the chat. We have that the sine of 60 degrees is the square root of 3/2. That is right. Look, everyone, that is the Y value there. Yes. And again, if you need any clarification, just let us know. That is correct. So again, you probably want to type this out on your own copy of the slides and or make yourself a little comment. Okay. Now for cosine, that means I'm looking at the X. Oh, and we're still at 60 degrees, so that's nice. So I'm still here, except now I just need to look at the X value. The X value or the remaining coordinate here is simply 1/2. Let me go ahead and stick that in there. And then we got sine of 120. That is next. So let me go ahead and erase. So for sine of 120, I want you all to just do this like mentally. I'm just gonna go ahead and put the answer for this one. But if you need me to explain it, please make sure you advocate for that. But here's the answer. Another thing you can do is you could go ahead and try to figure out how I got that answer. But the sine of 120 degrees is the positive square root of 3/2. So that is my examples. Let's see, are there any questions or clarifying questions before we jump into the next portion of today's lesson? All right, cool. So I'm gonna go ahead and transition us, everyone. Thank you so much for that. And let's go on. Okay, y'all. The unit circle and waves, finally. You have an essential question that you're going to be asked to ponder about today as you're working in a mini small group kind of discussion. It's going to be on Desmos. But the essential question is, how is the unit circle connected to functions that have waves? So how can we make this connection, right? All we know is that there's a unit circle and we know that things can move in a circular motion, like a Ferris wheel, or you can have a wheel, or even a windmill when we looked at the windmill last time. So let's go ahead and hold this question in our head. We will, at the end of this, try to create a response to how the unit circle is connected to function waves. Okay. So as a reminder, I showed you this on, I think, day one, our first day into this module, but I showed you that many things in the world can be modeled with trig functions as waves. And every repetitive vibration, you know, when you talk and when you're talking, if you were to put your hand on your throat, you feel it vibrating, right? These vibrations are causing waves actually to produce your sound. So this is another way. So as you see these vibrations, they create sound waves. So sound can be represented by waves. Next up, not only that, not only sound or color frequencies and things like that can be represented by waves, but also actual motion of an object, such as a pendulum swinging, a slinky going up and down, or even a Ferris wheel going around and around. So many other emotions that could be represented by a circular circle, such as a unit circle. So sometimes motion can be represented by waves. So that's just a little bit of a review on the real world application of this. So then, again, the essential question. Okay, great. We know that there's waves in the real world. We know that even right now, as I'm talking, as you're talking, these vibrations, they're creating air pressure in the molecules to create sound. It's the air pressure of the molecules that are making the waves. But essential question is, how is the unit circle connected to functions with waves? So this is the big question that I need you to think about today as you're working with your groups. So, I mean, feel free to look at the slide and kind of just already make some connections if you see them. But again, this is going to be a mini exploration. Okay. So, okay, short group Desmos. This will be for credit. I put participation quiz. I know y'all have done participation quizzes like a Miss Lawrence, but you know how it is. Like it's mostly like I'm not coming in to facilitate, more so I'm coming in to observe and just see how you all are interacting. Might look for. So I'm looking for screen sharing. So making sure there is a screen share. So if you aren't on your laptop, you can feel free to log into that right now and kind of come back in to make sure that you can screen share. I'm looking for interactions and questions, either verbally, right? Or sometimes people are more comfortable using the chat and checking for understanding. It's going to be for about 10-ish minutes. And make sure everyone's name is written on the Desmos for credit. Again, and once again, here is the prompt that your groups will be focused on. How is a unit circle connected to functions with waves? If groups are uncertain, you're going to jot down your notices or wonders. Let's see what's in the chat here. Yeah, it's okay. So yeah, we're gonna have to, yeah. So let's just see. Today's groups are gonna be a little bit random. Also, give me a sec. I actually just realized I gotta put this link into the Google Classroom so y'all know where to go once you're in your groups. So period 1, I'm going to go ahead and put the Desmos link right here. Group Desmos link. There we go. Okay, does anyone have any additional questions or anything before we jump into our breakout rooms? Once again, it's going to be for about 10-ish minutes, and it's a very short Desmos. And these groups today, it could be that you're not used to seeing everyone in your group. The reason is today is going to be kind of random. So there's going to be group roles. Make sure everyone's name is written there for the roles so everyone can receive their credit. Let me go ahead and open this up and start to assign anyone who's missing. Okay, so let me go ahead and just move people. Some of you are unassigned. If you see that you're in a breakout room, go ahead and join. Some of you I need to still assign, so give me a second. All right, join your breakout rooms. I think they're open now. Do y'all see an invite? So Maria, August, Niara, Aisha, let me know if you see it. Hello.
Hello. Where's the link for? Yeah, I found it on the slides.
Oh, you found it on the slide. Okay. Okay, cool. I just posted on Google Classroom too, but yeah, on the slide too. Yeah, my bad if that was a little bit confusing, but okay.
Thank you.
You're welcome.
This one's.
Hey everyone, just checking in on groups. Do we all know where to go for the link? And do we know who's screen sharing here today? So I know, Lali, you said you're not able to screen share. Kimberly, Bianca, or Maria, are any of you able to screen share? So I see Maria is not able to. How about Kimberly or Bianca? All right, we got Kim can try. Yes, okay, let's try that, and I'll be right back.
All right. Okay. So.
Hey, you two, this group is kind of small. Is either of you able to screen share?
I'm on my phone because my computer died.
Uh-oh. Okay, how about you?
Same. I'm also
Here's what we're gonna do. I'm gonna switch it up because this is a small group. So I'm gonna move you to another group, okay? That way it'll be a little bit nicer.
okay.
Let's see. So if you see a new invite, just click accept. I'm just trying to see which room has the least people so that you can switch there. What is this breakout room? This is breakout room. Do y'all see the number?
3.
Oh, 3.
Break
Okay.
out room 3.
Okay, I'm gonna move you to number 4 for both of you.
I'll let my brother know.
Hey,
He said that.
hey.
Oh, we changed people.
Yeah, so we added 2 more folks because 2 groups of people. So yes, let's just go ahead and yeah, adjust our thing. Sorry about that, y'all.
Who wants to be the timekeeper?
I can be the timekeeper.
Oh, that way.
Or do you guys have any idea what I'm talking about?
Yeah. So you're actually able to create like a triangle within a circle by the angle.
I mean something like that because what I'm seeing is when you move whatever I forgot what this thing stands for. It's like a zero with an R. I don't know, but then like basically you're like whatever the how do I say this like the circle. How do I say it? I guess like you're changing the shape of the circle or something. Like the length of the circle is going into the wave. I guess.
Yes.
So it says using the tool, you are able to create a sign function. How can your team describe what's happening now that you explore with the tool? Oh, it's doing waves.
So
Do
we
you
were kind
also?
of correct, right? Like it's inside the circle.
Yeah, I think like the is connected to the center of.
Which means that uh,
You said about the circumference that was very useful. Okay, what do you all think about this answer? Okay.
Yes, I agree with that.
Um,
Yeah.
how the unit circle? How the unit circle? How is the unit circle connected to functions with the waves? Connected to functions. How the unit circle connected?
Do you think that they have like an equation, like maybe like the equation is like connected? I'm not sure.
I think that's actually pretty good. The equation of the wave and the circle.
Yeah.
Hey group, how are we doing on this first one? Oh, okay, Kimberly, you're typing it in. My bad, just checking in here.
because like the length of the unit circle is being turned into a wave. Wait, Miss Alano?
Yeah, what's up?
Um, as for like for waves, so what I've seen is like it's like how the unit circle like can create like what is it called, like two waves or something? Because like I said in the very beginning that they look like two half circles like
Mhm.
being combined, like being split apart. Like do you just call them like, I don't know how to say it, waves, like the bumps, like
The
it's
bump.
like
I mean, you could call them maximums or minimums if you're talking about the high and low points.
yeah, like two of them, like I was saying, like a unit circle is basically like one full, like a full unit circle is one like maximum and minimum low
Oh,
point. Is that
yeah.
how I was?
Yeah, well, where would you say the maximum would be at on a circle? Would be like at what location?
Are you talking about like maximum of a circle?
Yeah, like if you're looking at the wave and like where the maximum point was at, right? Where would that be on the unit circle?
Wouldn't that just be at the very top?
Yeah, yeah. Go ahead and write that because you're making connections with the maximums and minimums of the circle and what you see what's happening in the wave.
Huh, Johnny, I hope you got all that.
It is hard to verbalize though. It is hard to verbalize. So it is.
Please repeat that before my mind goes off.
I should have written that down. Okay, let's see. The minimum and maximum of a circle. Just start off with that. Let me go back to, is the same as the minimum maximum of a wave. Um,
And then you said minimum. Oh no, go ahead. Actually, go ahead.
no, I actually don't know what else I was about to say. That's
You were
all.
saying something when I asked you like, so where on the unit circle would be the max, and you said the top, right? And then
Yeah.
you want to also tell us like where would be the min then on the unit circle?
You could just you could just like say like the maximum is at the very top of the circle while the minimum is at the very bottom of the circle.
Okay, that's a good pattern we saw here.
Yeah, because at the beginning it honestly did look like two halves of a circle. Like that's what we said at the very beginning. Turns out I was kind of right.
All right, yeah, that's awesome.
Wait, but then also one other question, because I forgot who asked this, but they said like technically, like could you use right triangles in this, or like how would this all work? Like how could like triangles fit into this?
Oh, that's a good question. Yeah, so you could use, yeah, can use triangles, but you would actually use an infinite amount, right? So if to get every single point on that wave, you would have to build a lot of triangles to actually recreate that. Um, but we don't have to do that. So like, for example, like when we're just looking at the coordinates, there's only like very specific coordinates, but we don't have the actual points in between those specific coordinates. So you could actually, yes, still build right triangles in there, but you won't be asked to actually do that.
All
Yeah,
right.
very good question though.
Would we be asked to do that later on in life? Like let's say we go to
No,
college.
no, you will not be asked to do that later in life.
Oh, okay, good. Because I remember seeing some math at UC Berkeley. I don't feel like doing any of that. It's a
No, I
lot
don't
of math.
yeah, I don't think you'll be asked to do that. All right, y'all, I'll be back. I'm getting asked for some help in a breakout room. You have one more question, and we're going to be coming back as a whole group soon.
All right, thanks.
Welcome. Hey, group. Oh, are we done?
Yeah.
Yay. Okay, cool. I'm going to actually start to bring everyone back now. So I think most groups are in that last question. So just hang out for a bit. We're going to come back super soon. And we're going to learn about the connections. Right, let me just check in on the other groups. Oh, y'all are done too? I'm going to go ahead and close up the rooms, everyone. I'm going to see you all in the main room. Let's go ahead and talk about all this. Thank you so much. Welcome, welcome. I am, oops, waiting for all the groups to come back so we can talk about this. Now, let me make sure I anonymize this so we can take a look at what we have. And I think it takes about a full minute for all groups to be back unless they click on the thing. Okay, I think we have everyone back. It says I have 21 folks back in. Welcome back, everyone. We're gonna go ahead and take a look at some of the ideas y'all had in this exploration and make some connections to what our big ideas are. So first off, in slide number 2, you were just asked to kind of take a look at this picture visually and just come up with some ideas on how in the world a unit circle would be able to create waves. They have different ideas here that y'all thought about. Some of them is like kind of like it looked like half circles kind of being connected together. And some had ideas that you can use. You can also use the unit circle to find the coordinates of the waves and so forth. So we had some beginning ideas. You were asked to then investigate with this very nice tool. Again, visual modules and math are so helpful. So here you were being asked, use this tool to see how a wave can be formed by something like a unit circle or any circle in reality. After that, you were then asked to go ahead and, oh, where's back my group? Okay, there we go. Then you were asked to go ahead and think about any new things you got from looking at that visual example. So we have, again, that half circle idea coming up. We have additionally that the circumference of the circle is acting as a guide to create the waves. Ooh, and this one says the height of the waves won't be higher or lower than the circle. So higher and lower than the circle. So see how the highest point right here, lowest point right here. And that was also mentioned in another group too. Go back to that. And that it can represent angles of more than 360 degrees. So this other group here also mentioned that thing that other group said. So this is Mina's group. The minimum and maximum of the unit circle is the same as the minimum and maximum as the wave. The maximum is at the very top of the circle and the minimum being at the very bottom. So two groups saw that connection. We see the connection on how a circle can be used to model waves. And then we have that circumference coming up again. We have that this graph can go more than 360 degrees, which is important. Kind of like you could keep going as far as your motion. Lastly, I asked you all to kind of compare these kind of graphs. So this one looks like a sine wave. This one looks funky. I don't know what kind of wave thingy that is. This is another kind of wave. And then you have some other kind of thing that's not a wave right here. But I asked you all to go ahead and put what did you notice or what was similar or different? I think only two groups got to this. We have some are rounder, some are different, some are negative. Some are bigger. One guess we have is the unit circle effects, what kind of waves look like. Okay, that's awesome. Wow. And then we have, oh, actually all four groups. Wow, y'all are great. It says the wavelengths differs from each other. So they're similar, following the same pattern, but it never differs. Then we have the two sets of waves cross the x-axis while the others don't cross. The shapes of the three are similar with minor differences. And they're all waves. They go up and down and have the same symmetrical pattern. Yeah, I don't know about this one though. This one doesn't, I mean, to me, it doesn't look like a wave. It looks like, I don't know, weird thing going up and down and up and down. We're gonna know what these are in right now as we wrap up in the big ideas. So first off, thank you all so much. That was great. Make sure that everyone's name was included in the group thing so I could give you all credit. If you're concerned, like let's say you were booted out and your name wasn't on the thing, just let me know and remind so I'll exempt you from that. So, okay, everyone. Let's go ahead and move on to slide 14 on the slide. Let's see what the big ideas are. So slide 14, I am back on our slide. Unit circle and periodic functions, big ideas. So a sine wave is formed by imagining a point on the circumference of your circle. So circumference was coming up in some of the groups. And what you're doing is actually you're tracing the height of that point over some input such as time. So over time or over degrees or over radians, some input, whatever the input is, right? So I'd like to think of this using a Ferris wheel. So let's say that you board the Ferris wheel here. Let's say that you get on here. So rider boards there. Then let's say over time, right, you're going to move counterclockwise on the unit circle like this. And over time, you're going to end up there. So you are the rider. What is getting mapped out? And again, there was a mention of it can't go a higher or lower than the circle or the maximum and minimums. So I'm going ahead and kind of labeling this right here as the height. So let's say you're down here. You as the height of the rider would be at height 0 feet. You're on the ground as you enter this unit circle. I mean, as you enter this Ferris wheel. Okay, so then you're at height 0, but then as you go up over time, your height is increasing. So what we're actually mapping or what the sine wave is mapping is your height over time. So take a look. And I actually, if you're on the slides with me, you could actually look at this tool. So a sine wave is formed by imagining that you have a point on your circumference, and this point you could imagine like a rider on a Ferris wheel, and you're tracing that height of the point over time. I like this little tool that's in the bottom of my slide right here. It's right here in the notes section. This is the thing I found to kind of exemplify this. So this is the Ferris wheel. And let me just clear my drawing. And I'm going to go back here. So see, you start at 0 minutes here. And then just trying to make sure y'all can see. There we go. And over time, so as I increase my minutes, me as the rider, I'm going up to the very top. So I'm at the very top of the Ferris wheel right here. See, that's a maximum. Then this moves really quick. Then I go back down, minimum. So right here, I did one cycle. I went once in the Ferris wheel. I went a full circle in the Ferris wheel. This was one cycle. Then I keep going. So I go back up, back down, back up, back down. And then let's say that was it, and they tell me I have to get off. It would have to end right here, let's say after 3 cycles. So after, in this case, a 9-minute, well, for that case, it would have been a 9.25 minute Ferris wheel ride. So that's exactly how the sine function is getting modeled, is you're mapping your height over time on the unit circle. So that is the answer to that question that you all were kind of thinking about and working on in your groups. So super cool. And again, let me know if anyone has questions about this that I just used to kind of explain that. Ferris wheel, just imagine that over time. Okay, let me go ahead and go over to the next slide, slide number 15. So what are these kinds of functions? Unit circles and periodic functions, big ideas. So functions that model any wave-like behavior actually have a specific name. It sounds weird. They're called sinusoidal functions, also known as sine or cosine. So sine is a sinusoidal function and also is cosine. Look how similar sine and cosine look to each other. They're very similar. They just kind of they're kind of shifted. It looks like sine is slightly shifted to the right, and then cosine kind of starts right there. I also want you to notice that your input can be radians or it can be degrees. That's why there's 2 numbers here. Either one would work if you were trying to use that as your input, like what is going into it. Or as we saw with the Ferris wheel, your input could be time. So there's different like ways you can input or graph this. And we're going to later on next week kind of see exactly how to graph these and what we can do with these waves when it comes to things like sound. So because we only have like a few minutes, I'm going to go ahead and take us into our checkout because I don't have enough time to do the remaining two big ideas justice, but you are free to check them out. If we don't have time to talk about them today, you could go ahead and review them and we'll talk about them coming back on Monday. It's slide 16 and 17. But let's jump into our checkout for now. So our checkout question is, what is a question that you have right now or what's coming up for you? Go ahead and put that in the chat for us. And I mean, this could be anything. It could be a wonder about like how we're going to use waves. It could even be a question about what the mini final is going to be about. Just go ahead and put your thoughts there in the chat as a question. We got, why is math so hard? It's doable though. Like you're very smart. Are we going to be using waves or doing them? That's a good question. I would say we would be slightly doing, but we're going to be mostly using. We're going to mostly be applying it. And what is the mini final going to have in it? The mini final, we're going to actually be, it's going to be about sound waves. And we're going to try to model the sound waves that we make. And I learned about waves connected to a unit circle. What other types of waves this is and what will they simulate? Oh my gosh, so the list could be endless. Check out Wikipedia, even though I know Wikipedia is not a trusted source, but there's like, if you look up like waves and their applications, there's like so much. Okay, that's okay. Are we going to do the waves connect to the, how does the waves connect to the circle? Okay, so we have a question about like today's essential question. Okay, and we're gonna talk a little bit more about that wrap up on Monday for sure. Are waves gonna be used to solving the unit circle? That's a good question. So I'm not sure about solving the unit circle, but we will be doing some solving later on when we have more tools. How can waves be used when the height of an object is not consistent? That is a good question. That is a good question, actually. Even when you're talking, right, our voice isn't always consistent either. So that makes me think about that mini final that we're going to be doing later on. So how we're going to record our sound and how, in fact, does sound and our voice travel through the air to make sound as waves. So that's a great question, Francisco. All right, y'all, any last burning questions before y'all head out? I know that you have a next class right up, so I don't want to take up more of your time. Appreciate you all. Have a great day. Bye, everyone. Happy Thursday. Bye.
Bye, Saddam.
Bye, August. Bye, y'all.